5 kilograms is released from point A and slides on the frictionless track shown in figure 8.4. Determine A, the particle speed at points B and C, and B, the net work done by the gravitational force as the particle moves from A to C. So, to find the speed at B and C, we define the total energy of the system. So we'll do B first. The potential energy, we can use the point at A to make it a lot easier since the kinetic energy at rest is 0. So mgh is equal to 5 kilograms, the mass of the ball, times gravity, times 5 meters, which is how tall A is. So in total, we're going to get 245 joules of energy. To find kinetic energy, we're going to take the total energy of the system minus the potential energy of the point at B. So at B, we have, again, the formula, 5 kilograms times gravity, but instead we have 3.2 meters this time, because that's how tall B is. So in the end, we get 156.8 joules. To find kinetic energy, we subtracted potential energy from total energy, so we get 245 minus 156.8, which was from here, to get 88.2. Setting it to 1/2 mv squared, we can solve for v and get 5.9 meters per second. So for C, we do pretty much the exact same thing. Again, we already know that 245 is the total energy of the system because we found it up here. So all we have to do is find the potential energy at C, which again is mgh, which is 5 kilograms times gravity times 2 meters equals 98 joules. The total kinetic energy is the total energy minus potential, which is equal to 147, and setting that to 1/2 mv squared, we can solve for v and get 7.67 meters per second. Now B, they want us to find the net work from A to C, and from the book we know that work is the change in kinetic energy. So 1/2 mv squared C minus 1/2 mv squared A, we can determine that the kinetic energy at A is 0 because, like how we did it up here, the ball is not moving at first. So velocity is 0, which makes this entire thing 0. So now work is just 1/2 times 5 kilograms, mass of the ball, times the velocity at C, which is 7.67 meters per second squared, which will equal to 147 joules of work done for the total system from A to C.